Hello students, welcome back. We're going to continue with proteins part 5. Let's do a little review of what we talked about last time. Really don't remember it that well. Let's see here. Yes, proteins part 4 is what we talked about last time. Yes. The last thing we talked about was size exclusion chromatography, or gel filtration chromatography, also known as molecular sieve chromatography. And what you want to remember here is you have these beads, and these beads have holes in them, these long passageways that go through them. If the particle is small enough, it's going to go into those beads and have to travel through all of those channels in those beads. And so it's going to take very small things a very long time to pass through a gel filtration column. But particles that are very large, if you have very large proteins, they're going to be excluded from the beads and they're going to pass through very quickly. That was the concept. That was the entire concept for last lecture. Does that make sense? Okay, very good. So now today, when we stopped last time, we ended up with which proteins? The large proteins. So now we've separated, let's say P was that we had a big P, a little x, and a big Y. Okay? Now, I can ask you all this question now. Of P minus, X minus, and Y minus. Now let's see if you understand it. Which protein is going to pass through the column first? Okay, somebody said X minus. Some say Y minus. Any other? There's only one choice. Anybody that's going to say P minus? The answer is going to be Y minus, because Y minus is the largest. It's never going to go into the beads. Does that make sense? And so let's say now after we've gotten all of our proteins off, we have P minus and Y minus. Those are the two proteins we're left with. So I'm going to grab here. Let's get P minus. Let's see here. And Y minus. I'm going to put these on a new column. Oops. Okay, here we are. P minus and Y minus. Doesn't want to grab it here. Oh, that's what I want. Okay, so we're going to bring this up here. Okay, we can get rid of this now. Okay, now we just have P minus and Y minus. So we have these two large proteins. They're two large proteins. Let's say they're kind of the same size. Now, how are we going to separate? Let's make this even more difficult for us. And so what we're going to do here, we're going to have P, and we're going to have Y. And we're going to make them about the same size. Now we have two proteins that have the same charge and they have the same size, and they're both in our sample buffer. How are we going to separate these proteins now? Can we use anion exchange chromatography to separate these two from one another? Why not? Why can we not use anion exchange chromatography? They have the same charge. Can we use gel filtration to separate them? Why would they travel the same? Exactly, because they're the same size. So now, how are we going to separate these two proteins? Does everyone see the problem we have? Now I'm going to explain to you how we're going to do that. How we're going to separate these two proteins. Now, at the beginning, let's just name any globular protein. I know what you're going to say. Name any globular protein. Tyrosine hydroxylase. Let's just say here that this protein we want here, let's say P minus, let's say it's tyrosine hydroxylase. And let's see if this makes sense to you all. Now, tyrosine hydroxylase. Let's see here. I'm gonna draw here. I'm gonna draw something here. I'm going to draw an amino acid here. Now, okay, should it make sense to you? What amino acid is this? Tyrosine. This amino acid is tyrosine. Now, what does tyrosine hydroxylase do to tyrosine? It adds a hydroxyl. Exactly. It's going to add the hydroxyl group. I'm going to make another layer here because I don't want to keep this here. It's going to add a hydroxyl group about right there somewhere. Make sense? So now, what scientists have done, in order to so I'm going to draw the protein over here. So I'm going to get rid of that hydroxyl group. Well, we can put it there because it's going to need to be able to do that anyway. So I'm going to draw the protein here. This is the protein, the enzyme, tyrosine hydroxylase. So tyrosine hydroxylase is probably going to look something like this. It's going to have a cleft here to bind. It's going to have to be able to bind tyrosine, right? And so let's say that this is the P- that we want to get. And so scientists said, wait a minute. This is how scientists are going to reason this. And let's just see if it makes sense to you. I'm going to explain it again, but just listen. They're going to say to themselves, why not make ourselves a bead, some sort of bead, or just get a bead, some sort of very small bead here. And what we'll do, let's attach tyrosine to these beads. And so this is going to be our big bead here. This is a bead here, and we'll attach tyrosine to this bead, or some sort of derivative of tyrosine. Some sort of derivative that the tyrosine hydroxylase will bind to. In this protein, let's say this protein here, the Y-, it doesn't bind to tyrosine. Okay, and so what the scientists will do here, they're going to make a column. And in the column, you're going to have these beads here. These big, huge beads. And on these beads here, you're going to attach the amino acid tyrosine. Or really, you don't need tyrosine. All you need is that phenyl part. You can add some sort of derivative of tyrosine. You don't care what this is. That the enzyme will attach to. Because we know the enzyme attaches to tyrosines because it turns the tyrosine into dopa. And so now, what's going to happen when you take your mixture, this is our mixture, and this mixture is going to have, instead of putting P- now, I'm just going to put TH for tyrosine hydroxylase. So tyrosine hydroxylase with its negative charge, it's going to have this protein, and it's going to have our Y- protein. What's going to happen when you add tyrosine hydroxylase and this other negatively charged protein to this column? Okay, I want you to think about that for about 3 seconds. 1, 2, 3. Does anyone think he or she knows the answer? Okay, read. What's going to happen? Exactly. What's going to happen here, now the tyrosine hydroxylase, when it gets here, it's going to bind to this because it looks just like the tyrosine. It looks like the tyrosine. So the tyrosine hydroxylase is going to bind here, and the tyrosine hydroxylase is going to bind here. And what's going to happen to the Y-? The Y- is just going to pass straight through the column because it has no affinity for that substrate. And now we've separated the tyrosine hydroxylase, or whatever the enzyme is that you want. You separated it from all the other proteins. Does that rationale make sense? Winters, does that make sense? Ooh, let's go over it again. Let's go over it again then. Okay, I want this to make sense for everyone. So let's go back and let's see what we have. And so before we started out, we had two proteins. We had P minus, which is our tyrosine hydroxylase, and we have Y minus. We can't use anion exchange chromatography because they both have negative charges. We can't use gel filtration chromatography because they're the same size. So we need some way to separate these two proteins from one another. And what we'll do then, use the function of that. Let's exploit the function of that protein we want. The protein that we want, tyrosine hydroxylase, we know it has to bind to tyrosine. So if we can attach tyrosines to some beads and make a column that has tyrosine sticking off the side, then our tyrosine hydroxylase is going to bind to that column. Does that make sense, Winters, kind of now? And so now when we go here, when we make this column, there's our bead, there's our phenol ring that has, or the part of tyrosine that it's going to bind to. And so when we put the tyrosine hydroxylase and another protein on that column, the tyrosine hydroxylase is going to bind to whatever looks like its substrate. It's going to bind to it and it's going to stick. But this other protein, Y minus, that doesn't bind to tyrosine, it's going to pass through the column. It's going to pass through. Does that make sense to everyone? Okay. Now we've separated tyrosine hydroxylase. We've separated tyrosine hydroxylase from the Y minus. Now the question. Shaw, this is the question. How are we going to get what is the name of the process when you remove the wanted material from a column? What's that word? Elution. That's the word. Now, how are we going to elute the tyrosine hydroxylase from this column? This is a tough one. Okay, let's do it this way. Did you come up with it? Let's do it this way. I need everybody to think about this. For 3 seconds. One of you will know the answer. You just have to think. How are we going to get the tyrosine hydroxylase? How are we going to elute it from the column? How are we going to induce the tyrosine hydroxylase to release those tyrosines, to not bind to those tyrosines? Okay, everybody think about that for 3 seconds. 1, 2, 3. One of you, I hope one of you can give me an answer. One of you should be able to come up with something. Nobody? Okay, read. Okay. That's okay. She said we can introduce some agent to alter the phenol ring so that the tyrosine won't bind so to chemically modify the phenol ring so the tyrosine won't bind. That would work. That would possibly work. But if the tyrosine is already on it, how would it get in there to it? And so that may not work. But I like the way you're thinking. Say that again. Now, if you can add an acid to make things either positive, to add a proton, if you add an acid, it's going to make things more protonated. But a lot of times, your active site is not really charged. It's not polar at all. So adding an acid to the active site won't really do a lot there. Yes. Okay. You could raise the pH, but that's what she said, or change the pH. That probably won't work. But changing the temperature. But the only thing is, when you're working with globular proteins, if you start raising the temperature, you can affect the activity of that protein. The protein will become non-functional. But y'all are thinking somebody's going to give me that answer. It's an ingenious answer. Yeah, you could add high salt, but a lot of times that active site cleft is not very polar. So adding a salt, there are a lot of hydrophobic interactions right there. But there is, except where the substrate binds, that can be polar. But the thing is, it's closed off from the aqueous environment, so water and salts wouldn't even get in there. Come on, some person. That is the answer. That is the answer. He said it. You add more tyrosine. If you add tyrosine, now during equilibrium, when every time that tyrosine releases and binds, now the tyrosine is going to come to there and it's going to bind. Does that make sense? Does that make sense to everyone?
Okay, so you're adding some of the protein or some of the protein that you already want to this?
No. You're adding the substrate. Add more tyrosine. Whatever you put to the bead, add that. Now it's going to bind to the stuff that's just flowing through, and it's going to flow through with it. Isn't that ingenious? Very good. Very good. Excellent. Okay, and so this is going to be, what you're going to do here is add more tyrosine. So here, to elute, you elute with whatever your binding agent is. You may not want to use, elute with binding agent. And I'm going to ask you all something in just a second. That was an excellent answer, Taylor. An excellent answer. Okay? Now, when you make this column, I just want you all to think. Everything about biochemistry is just thinking. You can think your way through anything. When you make your column, you wouldn't want to actually use tyrosine to bind to the bead. You want to use something that's similar to tyrosine, but not tyrosine itself. Why not just use tyrosine? Okay, let me ask you this then. What happens, let's say you had a presynaptic nerve ending. What happens when tyrosine comes into a presynaptic nerve ending and it attaches to tyrosine hydroxylase? What does it do to it? It's going to become DOPA. Okay, now why would you not add tyrosine to your beads? Right, tyrosine uses one. Yeah, tyrosine has one OH, but why not attach tyrosine to your beads? It's going to convert it to DOPA, and then it's going to release it. And so it wouldn't stick to the column. It would just convert it to DOPA and go down. Now anything else that's coming later wouldn't even bind to the column. So you wouldn't use tyrosine. You're going to use some chemically modified version of tyrosine that will bind to the tyrosine hydroxylase but wouldn't let it go. Make sense? And so that's why I say, it's going to be some sort of chemically modified version. And so whatever that is, now let's say you want to elute the tyrosine hydroxylase from the column. Would you use the chemically modified agent to release it, or would you use tyrosine to release it? Why could you use tyrosine? Exactly. You could use tyrosine because it'll convert it to DOPA and release it. It'll go on down the column. Or you could add the chemically modified version. It doesn't matter then, but you could use tyrosine in that case. Does the reasoning make sense? That's all I care about. Does it make sense?
You would have to use something else besides tyrosine?
Yeah, to bind to the beads. Exactly. A lot of times when you're making something that binds to a substrate, what happens when an enzyme binds to something, it converts it. It has to take that substrate through, what do you call it here? It has to go over this thing called an activation energy. And so that intermediate product, the intermediate between the product and the substrate, that's called a high energy intermediate. You want to make something that looks like that, kind of. And so that's what they normally do. Right, some sort of alternate substrate that it'll bind to but won't release. That's the best thing to use. And then, when you get ready to elute, you can add a very high concentration of tyrosine or a very high concentration of whatever you put on the column. Now, we need to give a name for this type of chromatography. Okay, we've had anion exchange chromatography, and we've had, what else have we had? What other type of chromatography have we had? We had anion exchange was the first type. Then we had gel filtration. And this type of chromatography is called affinity chromatography. And that makes sense, doesn't it? Because your protein is going to bind with affinity to whatever substrate it binds. Okay. Now, I'm going to ask you all a question just to see how much you understand something. What if you were trying to isolate the beta 2 adrenergic receptor? Let's say you've gone through all of the steps. You made the precipitate. You went through anion exchange chromatography or cation exchange chromatography. You went through gel filtration chromatography. Now you wanted to isolate the beta 2 adrenergic receptor from all the other membrane proteins. And you wanted to use affinity chromatography. What would you attach to the bead? Think about it. You have the beta 2 adrenergic receptor. Okay, let's go here. Here we have the beta 2 adrenergic receptor. You've precipitated it. You've gone through anion exchange chromatography. You've gone through gel filtration chromatography. Now you want to isolate it. Now your mixture has lots of different types of membrane proteins. Just a mixture of them. How do you separate your beta 2 adrenergic receptor from all the other membrane proteins using you want to use affinity chromatography to separate your beta 2 adrenergic receptor from all the other membrane proteins. What would you attach to the column, or a derivative of what would you attach to the column? Think about it for 3 seconds. 1, 2, 3. Anybody think they have it? Excellent, excellent. We have here, she said norepinephrine. So some sort of derivative of norepinephrine, and that would. But since we have the beta 2, but remember, norepinephrine, it can bind to alpha 1, alpha 2, beta 1, and beta 2. What would be a better derivative than even norepinephrine? What was that? No, G inhibitors are going to bind to a lot of things. What drug would bind more specifically to beta 2? Epinephrine is going to bind to all of them. What was that? Albuterol. Albuterol. Remember, it has that big amino end, so it's going to bind more specifically. I didn't really care if you got the answer right, but your thinking is right. That's all I cared about. You were thinking along the right lines. But does everybody see the rationale of using affinity chromatography? You just find something that the protein binds to and make an affinity column using that. So when you get ready to take your test, do you think I'm going to ask you about the beta 2 adrenergic receptor using affinity chromatography? No, I'm not. Think I'm going to ask you about tyrosine hydroxylase on the test? No, I'm not. But I'm going to ask you about something, some protein that we've already seen, just to see if you understand the process. But if you understand this, you'll be able to reason the answer when you get to the test. Make sense? Winters, make sense? Excellent. Excellent. Okay. Let's see. Should I go to the next one? Put your notes away. Let's see. I don't even have. Oh, I'll just turn this off. Okay. Let's see here. Tyrosine hydroxylase converts tyrosine into what? Into what? Dopa. Exactly, dopa. What's the difference? On which carbon of the phenol ring do you add the hydroxyl group to turn tyrosine into dopa? Which carbon on the ring? There are only 3 rings. Well, it can only be 2 or 3 or meta or no ortho or meta because it's already on the pair. Which one? Is it 1 or 2? Or you can say meta or pair or ortho or para. Which OH do you add? Which carbon of the phenol ring do you add the OH to convert tyrosine into dopa? Three. It's 3. Because it looks like this. So if you already have something here, and so if this is a phenol ring, if this is 1, this is ortho, this is meta, and this is para. You all remember that, right, from organic. And so, so that means if this is 1, if we're saying this is 1, we already have a hydroxyl here. This can be 2 or 3. You can only add it to 2 or 3. Why can't you add it to, if this is 2, 3, 4, why can't you add it to 5? Why can you not add it to 5? Who said it? Somebody said it over here. What'd you say? Yeah, 2 and 5. Not 2 and 5. 3 and 5 are the same. So you can't add it to 5 or 6 because that's 2 and that's 3. And so you can only add it to 2 or 3. 2 or 3. And you add it to here. You add it to 2. To 3. Make sense? Or meta. Let's see here. What other question can I ask you all? Oh. What is the name of the type of chromatography where you separate something by size? Gel filtration. What's the name of the chromatography where you separate proteins by the specific binding to a substrate, or affinity chromatography? And what's the type of chromatography do you use when you separate proteins based on their charge? It's going to be ion exchange now, not, well, if I said negative charge, you would say anion exchange. If I said positive charge, you would say cation exchange. But if I just say charge in general, it's just ion exchange. Make sense? Okay. What is let's say, this is a tough one. We're going to go after this one. This is the last question. Let's say you have a mixture of membrane proteins. And you want to use affinity chromatography to separate your beta-1 adrenergic receptor. What drug or derivative of what drug would you place on the bead? Isoproterenol. Have a great day, you all. Very good. Very good.